All right, so that is just an example, and let's do more practical thing, something we can compute. My favorite problem, remember that? Distance from a point to a line. So a new way of thinking about it, well, actually, we talked about it. Speaking of geometric approach, if you think about the distance function, and if I give you the point P, then you know what the distance function is. If P has, let's give it some coordinates, 2, 1. The distance to this point is the square root of x minus 2 squared plus y minus 1 squared. So this is distance from P to the point x, y. And now we can look at this expression as a function of both coordinates, as a function of two variables. And then what? Then geometry suggested that solution comes when that circle touches the line. What does it mean to touch?
Touch only at one point.
They share one point, and the tangent line to that circle is exactly the given line. So if you have that line, let's say in the form ax plus by equals c, or in any other form, you claim that at this point, the point you are interested in, the tangent line to the circle is equal to that one. So that's the key property. Tangent line to, well, to what? How to describe that circle? What is that circle? That circle is the level set of that function. It is the set where this function takes the same values. And when we do talk about the tangent line, we do this linearization. So algebraically, what happens is that we have to think about this unknown point, x0, y0, where the touching happens. Then at that point, we have to linearize that function, and let's call it f of x, y. So tangent line to the curve. So what's the equation of the curve? The equation is f of x, y equals a constant, which is f of x0, y0. We don't know what these numbers are yet. But you look at this equation, a function equals constant, it gives you a circle, and then we have to take that equation, linearize it to get a tangent line at that point. How do we linearize? Well, we bring both terms to the left, just to make it something equals 0. And then we what? We differentiate. And we take partial derivative of the left-hand side. What's the partial with respect to x of the whole left-hand side? What's the partial with respect to x of this? One? Who gives more? Partial of this expression with respect to x is 1. It is 1. It is 1 solved. The partial with respect to x goes to Joe. Joey gets partial as a bonus point 1 point. Nobody gives more. Is that how we do mathematics? Well, give me something. What do you think the partial derivative is of that expression? Of this one? Because I know what the partial is of this. It is fx. I don't know the explicit expression, but that's what it is. At least that's what notation is. What's the partial of that?
fx, not x not 1.
No, I asked for partial with respect to x. As you see, this is what we are doing. Partial with respect to x. Not partial with respect to x naught. Right? So,
X.
what is partial? What is partial of this with respect to x? It's constant, isn't it? It's a constant. It's value at some unknown point, but it's a constant. So the partial of that, well, there is no x there. There is only x naught, but x naught has nothing to do with the variable x. Right? So the partial of this is 0. So this is the partial of the whole equation, and that's going to be the, well, it's going to be used to compute the coefficient, the coefficient a in the linearization. All right, so a is fx at x0, y0. And what about partial with respect to y? So this is partial derivative with respect to x of the whole thing. Now what is partial derivative with respect to y of the whole thing?
Fy, xy,
Is
minus 0.
fy of xy, and if you allow me not to write minus 0, then this is what the partial is. And then b, the second coefficient, is going to be that partial evaluated at x0, y0. And now as I found those two coefficients, I can write down the equation of the tangent line to that red unknown get circled. So the tangent line has equation fx at x0, y0 multiplied by x minus x0 plus fy at x0, y0 multiplied by y minus y0 equals 0.